Okay, so how is everyone today? Good, I hope. Okay, so last time we were talking about substitution. So let's do one more of those. So, like among magicians, that is to say, stage magicians, it's considered impolite for one of their number to reveal how the trick is done. That's like, it's impolite in those crowds. So now what I'm going to do is I'm going to show you, in a sense, how the trick is done for substitution. And most other instructors I find say, "Oh yeah, that's a nice thing," but actually, I actually have had some that are just like offended that I do it. So here it is. In fact, we did an exercise. I posted an exercise just like it for WEX. So let's do one. So in that WEX, I said something like in Math 1326, we know the following antiderivatives. We know the one that looks like antiderivative of u to n du when n is not -1. This one we call the power rule. It is u to n plus 1 over n plus 1 plus a constant. The reason why n can't be -1 is because in the right-hand side of the formula, that would cause a division by 0. For the specific case of u to -1, we have a rule that covers that as well. What's the rule? Absolute value. And then plus a constant. Okay, so then in fact we can antidifferentiate u to n du for any n whatsoever. The last one that we know is antiderivative exponential of u du, and it is exponential of u plus a constant. So those are the three that we know. So every single antidifferentiation exercise in Math 1314 or Math 1326, every single one that we do, you have to exit through one of these 1, 2, 3 gates. Otherwise, if you're going to answer successfully, it must end with one of these. All right. So now we're going to see how do you make a substitution exercise? Okay. So I'm going to choose one. And in the WEX, I chose the logarithm one. So I'll choose a different one here. So I'll choose, just for sake of definiteness, u to n du with a specific n. So how about with n equal to, say, -3? That is to say, u to -3 du. We have chosen that one, and now we'll choose any reasonable function. U is some function of w. So now we just want to, pick something that's mildly entertaining. Function u of w. So how about, say, u is exponential of, say, u squared. No, it needs to be w. U can't be on both sides. w squared plus 1, and then like plus 8 or something. So that's some nice function u. So then now, this is where in the WEX exercise where you take over, it says, okay, now calculate du dw and du. That is to say, find du dw and then solve for du. All right? So du dw will be derivative with respect to w of all that mess. So the plus 8, you know, the derivative is additive, so the derivative in a sense just, you know, will hit the 8 by itself, and because 8's a constant, what's the derivative of 8? Maybe 0 this time, right? Because the derivative of 8. Derivative of 8 is 0 because it's a constant. So then, to that extent, we can kind of ignore the 8. To differentiate exponential of w squared plus 1, we'll need to use what? The chain rule, right? We'll need the chain rule because, well, the differentiation symbol is w, and that I'm covering up is not exactly a w. The fact that those are different means that the action of the chain rule will become apparent. So just to remind us, we're doing something that's going to look like ddw exponential of, say, z. And here I'm just ignoring the plus 8. So the derivative will be exponential of z. So if that z was a w, then we'd just stop, because there'd be nothing more to say. But because it's because it's different, the chain rule becomes apparent. So then we also get a dz dw. So that green bit that I just wrote, that's the action of the chain rule, a consequence of that w and z being different. Okay, so now differentiate. So this, the red just says just copy whatever that is. So then exponential w squared plus 1, and then now multiply by dz dw, right? Which is to say the derivative of w squared plus 1. So those two green parts are analogous. Any question about getting here? Yes?
Okay, back to the very beginning when you said this covered the chain rule and covered that part of the equation.
Mm-hmm. That?
Yes.
So what I'm saying is I'm covering up z.
Okay. But your basis for using, you said something else about chain rules. Is it because the...
Well, let's say it like this. If this was a w, meaning that that and that are both w's, so they're in agreement. That's as opposed to this situation where one's a w and the other's a z.
This is just for when you're figuring out substitution.
This is just chain rule. This is differentiation. So this is to that extent calculus 1 material.
Right. Okay. Problem. I get that. I just was. I think I was overlooking what you did there. I missed something else here, but no.
Okay.
Sorry.
So then, to finish this thought, this would be e to w. And because these are the same, it's not necessary for me to write an analogous green part. But even if I forgot that, or just expunge that knowledge from my brain, I could still go on to write what I'd have to write, which would be dw dw. But the thing is that dw dw is 1. So this dw dw has no effect, whereas this dz dw does. Okay? So carrying that out, this would be e to w squared plus 1, and then multiplied by 2w. And again, I want to stress that we're not solving an exercise right now. We're making an exercise. You know, it's not that we're answering a question that was given. We're constructing a question. So this here is du dw. So now we want to solve for du. So how do you solve for du? We just put the dw on the other side, right? So that we'll have du is exponential w squared plus 1 times 2 times w times dw, like so. Okay, now we're going to substitute u and du into the thing that we picked at the beginning, into that, so that we get antiderivative of u, so that would be exponential w squared plus 1 and then plus 8, all to negative 3, and then multiplied by du, which is all that mess, exponential w squared plus 1 times 2 times w times dw. And so now we can make it look slightly different. What I'll do is this is a perfectly reasonable way to write it, but I'm going to write this as a positive exponent by moving it to a denominator, and like this, so that the result looks like this. Exponential w squared plus 1 times 2 times w over exponential w squared plus 1 plus 8, cube that, dw. So there, we made an exercise. You know, and you could go into like the exercises for section 7.2. You know, there's like 80 of them. This one is, I would say, you know, probably like close to item 50. You know, in difficulty. Like if they you know, increase in difficulty as you go on. Like this one would be like around number 50 or 60. But literally every single substitution exercise is made this way. They're all made this way. All the ones that have an answer. Anyway. So like you know, just you know, to stress the point even further, I make exercises for y'all, and they're literally made with a program that I wrote that does exactly this. I select some u, and then I have the thing calculate the derivative, and then I do exactly this. Pretty fun, huh? So now, I do really mean that they all have to be made this way. The reason is a little bit technical, but I'll share it with you. The reason is this, that derivative and antiderivative are inverse to each other in the same kind of way that log and exponential are inverse to each other. But the thing is that exponential exponential and log are far simpler than derivative and antiderivative, because the kind of thing that you input to a logarithm is a number, but the kind of thing that you input into a derivative is a function. So because the input is so more complicated, that means that the derivative is more complicated. So derivative is a kind of thing called an operator, and the derivative as an operator has a property called closedness, so it's closed, whatever that means. I promise you I'm not deceiving you. And as a result, because the antiderivative is the reverse, the inverse of derivative, that means that antiderivative cannot be closed. So if you have an operator that's closed, its inverse can't conceivably be closed. What that means is that, what those two things mean is that you could write down any old function you want, anything that you could conceive and imagine, and you can calculate its derivative. It'll work. That's fine. You'll be able to do it. No problem. But if you just write down any old function that you can conceive, it is extremely unlikely that you'll be able to calculate the antiderivative. I don't mean that like you don't know how, but you might learn later. I mean that not possible. That's what I mean. So all of the antiderivatives that you're given have to be carefully constructed so that I don't accidentally give you a question that has no answer. And I'm telling you that this is exactly how they're constructed. So now you've seen how every conceivable exercise of this kind is constructed. There's no other way. Beautiful. Any questions before we move to something else? Okay. So now we're going to do something that's going to seem non sequitur. What I mean is we've been talking about derivatives and antiderivatives, and now I'm going to talk about something that, at least at first, I suspect will seem entirely unrelated. Okay, but I promise that there's a reason. Also, for those of you who've taken a calculus course before, where antiderivatives were discussed, great. I hope that you've taken notice that I refer to them as antiderivatives, and do not ever use the I word. So by the end of today's lecture, I think it'll be clear, I hope it'll be clear why I am not using the I word until now. So this is section 7.3 called area and integral. The I word. Okay, so before we embark on area, I need to just briefly remind you of some things that the state of Texas assures me that you already know. This is called summation / sigma notation. Okay, so, well, here's something. Can you imagine that it might come to pass that this might be an interesting thing to consider, in your musings? So like maybe you wanted to sum up 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared. I'm just trying to write enough of these to where it's boring. Have we gotten there? Okay, good. So that's, that's kind of boring, right? And then you can imagine, we could go all the way, instead of stopping at 12, we could stop at 1,326, right? Go really far, and it would be exceptionally boring. Well, as it happens, it is useful to be able to consider things like this, and it's especially useful to be able to write these in a compact way. So here's the thing. Notice that we're adding all of them up. So it's like there's 1, 2, 3, 4, 5, 6, 7, 8 terms. We want to add them all up. And furthermore, notice that this base, 5, 6, 7, that's what's changing, but all of them are being squared. So here's a slightly easier way to write this. you write this symbol, which is Greek letter capital sigma. Then you use an index, so I'll use I for index for I equals 5 to 12. And then I squared. So what that's saying is that, okay, I is going to range over the values 5, 6, 7, 8, 9, 10, 11, 12. That's what 5 to 12 means. You're going to take that I, and you're going to square it, and you're going to sum all those up. So what I'm saying is that this and this are identical in meaning. Now, a reason why this notation is useful is because, well, what if we went, from like I is 5 to 1326 and write I squared? Now this notation is, I would say, even far more preferable, right, than attempting to write out all those terms individually? Sure it is. Okay, good. So any question about this so far? So the reason to use capital sigma in the end is because the Greeks, they exist, right? And they have their own alphabet. And this is a summation. And the Greeks, even though they don't speak, they don't use the Latin alphabet, which is what we use. The English alphabet is derived from Latin. Nevertheless, they want to make S sounds. What Greek letter makes the S sound? Sigma. And this is a summation. Okay, that's the whole reason why. Okay, fine. So then, what if I write something like this? What if I say, I don't know, something like 1 over 3 plus 1 over 4 plus 1 over 5 plus, and then we take this all the way to like, 1 over 26. Would you please write the corresponding sigma notation, please? Okay, well, capital sigma. And then, just so you don't get too emotionally attached to I, I'm going to use a J. So, where should the index begin? At 3. And how far does it go? To 26. And then, in terms of the index, what is the expression we're summing? 1 over J. Okay. Any question about this? Okay. So just the briefest reminder that segmentation is a thing and it exists. Okay. So now, for the next several tens of minutes, we're going to go with the fiction that we have no idea what a shape is. It's gone, right? The idea of a shape is gone. So the idea of shape and area are gone. But what we do have is we have signed linear measure, which is to say that more or less that we know what a number line is. So if we have the convention that the number line is increasing to the right, if we mark out 2 points on the number line, A and B, then If we travel from A to B, then that travel is in the positive sense because it's in agreement with the increasing direction. And if we travel from B to A, then we're traveling in the negative sense because it's pointing in the opposite direction of the world. And you know, the signed distance from A to B would be B minus A, final minus initial. And this particular quantity for this particular picture, would it be positive or negative? It'd be positive because B is the greater. Or if you like, when you go from A to B, you're traveling with the current. See the arrow? So that'd be positive. And then going the other way, A minus B, that would be negative. So B minus A and A minus B, in fact, it's not just that one is positive and one is negative, that they are in fact negations of each other. So if this one is positive 5, then that one is negative 5. If we're only interested in the magnitude and not particularly concerned with the direction of travel, then we can always pick out the magnitude using what? Absolute value, right? Okay, depending on the context, sometimes you're interested in just the magnitude, sometimes you're interested in the signed magnitude, sign distance. So like when you're talking about traveling on the road, usually you're just interested in magnitude, in the sense that if it's 180 miles from South Dallas to North Houston, then if you were traveling from North Houston to South Dallas, it wouldn't be negative 180 miles, right? It'd be 180 miles. Okay. So we have signed linear measure, and we also have angle. Angle, which is to say that we can take two line segments that meet at a vertex, and we can measure this angle. And in particular, we know what a right angle is. So these are the only things that we know, but the concept of shape and area, they're just poof, gone. All right. So now we're going to define. Suppose that we have 4 line segments, and they're consecutive in the sense that they're like this, and moreover, they all meet at right angles, like so. So all those meet like that. Then we can import the other notions that we have from geometry, which says that, oh, okay, that means that these opposite pairs of lines are parallel, and furthermore, opposite pairs of such lines must have the same length because of various geometry things. So that would mean that if this one measures A, then this one also measures A, and if this one measures B, then this one also measures B. This shape is interesting enough that I think we're going to have to give it a name. What do you want to call it? Rectangle. That's a great idea. Let's call it a rectangle. Now, we want to give a notion to how much paint it would take to paint this rectangle. Now, if it took exactly a gallon of paint to paint this rectangle, does that mean that every conceivable rectangle that takes a gallon would be exactly this one? No, right? Because you could make it real tall and skinny. Like super tall, like a mile tall, but really skinny. And you could arrange it so that that takes a gallon, but you could also make it really flat. You know, just like lay the tall and skinny one on its side. Okay, we want some kind of measure that more or less describes how much paint it would take to paint the thing. What name do you want to give that measure? Area? That's a great idea. So, area. And again, we're just defining things now. We define the name of this shape to be rectangle. We define the name of this measure to be area. So now let's come up with a formula for it. What's going to be the formula for it? Oh, I think that's a great formula for it. Terrific. Good. So now we have a definition of a shape, rectangle, and we have a formula for its area. Now I'd like to point out some things. So the area of this rectangle is AB. What about the area of that rectangle? Also AB. What about the area? What about the area of that rectangle? Also AB, right? What about the area of that rectangle? Also AB, right? So what I want to establish for you is that translating it around doesn't modify the area. Rotating it doesn't modify the area. So area is a rotationally and translationally invariant quantity. So we can move it around. Okay? Fine. So now we know what a rectangle is, and we know what the area of a rectangle is. So I have a question. Now, this shape that we have here, suppose that again, all of these are right angles. So these are all right angles. Is this shape a rectangle? It isn't, right? It isn't. It's not a rectangle. But it seems to me sort of reasonable to say that this looks like something I could paint. So even though it's not a rectangle, I kind of, my intuition is telling me that it seems like this thing should have an area. How can we calculate its area? Right, we can cut it up into pieces, right? Because we could take this and cut it like right there. And then now do you see, oh yeah, it's not a rectangle, it's actually just two rectangles. So we could take these and we could separate them into two pieces, each of which are rectangles. And the thing is that having separated them, that doesn't actually change the area, because we just established that translating the areas around doesn't change areas. So now we have two rectangles, and we can find the area of each one and then add them up, and we can find the area of this thing. Right? Now there's nothing special about 2. I think you can imagine that I could draw another shape that was not a rectangle, but in fact could be decomposed into 3 rectangles. So I'll just let you use your imagination there, right? Or even 300 rectangles, right? Okay. So, you know, we could say, oh yeah, this is A, this is B, and this is P, and this is Q. So then, therefore, the area would be AB plus PQ. All right, fine. So if I was to give you any shape that could be cut into finitely many rectangles, even if it was a lot, then you could find the area of that shape. Okay, how about this shape? So now, again, it's constructed of line segments, but there's only 3 of them, and none of them are meeting at right angles. So this couldn't possibly be a rectangle. And furthermore, because none of the angles are at right angles, there's no way we could like cut it into pieces that are rectangles. Nevertheless, my intuition is kind of telling me that this looks like something that I could paint. Okay, so this 3-sided figure is useful enough that I think we ought to give it a name. What do you want to call it? Triangle. Okay, that's a great name. Now, being more serious for a moment, yes, we all do know the formula for the area of a triangle, right? Half base height. Why should it be that? You know, did Miss Harris in 2nd grade just like by fiat, by command, by royal authority just decree that it's half base height? Well, in what way? Well, the area of a rectangle is base height, right? Base times height. And so the area of a triangle is half that. So somehow, it seems reasonable that it must be half base height in some way. Let's do it. So I'm going to make a copy of this rectangle, or triangle, I mean.
My second grade teacher was named Mrs. Harris.
What?
Had her for second and third grade.
So that's supposed to be an exact duplicate, but okay. This is what we're going to do, is I'm going to, because we know what angle is, that also means that we know what the word parallel means. So here's a thing here. So this is parallel to that longest side of the triangle. And what I want is I want to move this line that way, keeping it parallel to that line. And I want the triangle to be contained entirely in between the two parallel lines. So notice that the triangle currently extends beyond it, so I need to go further, 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 further. So this would be good out here. But I don't want the lines to be that far apart. I want them to be as close as possible. So can you see that I could take this and come closer, 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 and just rest right on that point there? So I want that's the line segment parallel to that one that I want. So I'm going to draw that in. Okay, so I drew it in. Terrific. Now, here's what I'm going to do, is that from this new one, I'm going to draw down to this one, but at a right angle. So that's a right angle there. I'm going to draw down to this one, and that's at a right angle there. And so now, what I want you to see is that, if I was an excellent drawer anyway, that this here is a rectangle. That's a rectangle. So we could find its area just using the same way that we did with the other ones. Okay, calculate its base and its height. So let's say that this turns out to be B, and this turns out to be A. So the area of this rectangle that our triangle fits inside of, this is called a circumscribing rectangle. This area is AB. But now here comes the trick, and that is that I dropped this down and that one down, and I'm going to drop one more down. I'm going to drop this one down here. And now, I'm going to shade in the part that is inside of our rectangle, but not inside of the triangle. And what I want you to see is that, just looking at this part now, just that part, that's a little rectangle, isn't it? And moreover, the shaded triangle and the unshaded triangle, what about their areas? They're the same. They're the same because I could take some scissors and cut out the shaded one, say, and then rotate it, and it would fit exactly on top of that one. So, so that means that the shaded triangle and the unshaded little triangle there, whatever their areas are, they've got to be the same. Furthermore, I'll shade in this part now. And now just considering that, this bit is a rectangle, and the shaded and unshaded triangles, they have the same area, in the sense that I could cut out this shaded one, give it a twist, and it would fit right on top of the other one. So whatever those areas are, they have to be the same. So what I'm telling you is that the original triangle is this unshaded bit, and we've managed to fill in a rectangle that has to be exactly twice the area of the unshaded bit, because for that part it has its counterpart, and for that part it has its counterpart. So what's the formula for the unshaded area? Half AB, right? Because half of the rectangle is shaded. Okay, so Ms. Harris was not you know, legislating from the throne, right? not fiat, right? Apparently there was some reason. Okay. Fine. So that means that I could do something like this. I could say, okay, well, what if we take almost a rectangle? And so I drew 3 sides, almost a rectangle, and then now I'm going to put some kind of like a party hat on it, because this shape's going to get dressed up for the party. And like this, say. So now, is that a rectangle? No, it's not a rectangle. Is it a triangle? No, it's not a triangle. But can we agree that we could cut it into pieces that are rectangles and triangles? So that, you know, there's a rectangle, there's a triangle. Using the methods above, we can find the area of each, find the area of the whole thing. Okay. But then now I'm going to wreck the whole thing, and that is that what if I say this? What if I say, okay, this one's counterpart also wants to get dressed to go to the party, and this one gets dressed with a super fancy hat, like that. So now that's curvy. None of it's flat. See, the thing is that this party hat just consists of 2 flat pieces, 2 line segments. So that one makes it kind of easy. Whereas this is a curve. So now I drew it as if it's a differentiable curve, which means that if you zoomed in close enough, it would look flat. But it's not flat. So that means that you couldn't possibly cut this shape into, say, like 3 rectangles, or 2 rectangles and a triangle. It could never be right. Nevertheless, we want a formula for the area of this shape. Okay? So now, so we could carefully now go down the list of every shape that you've ever heard of. And I could just, you know, using various techniques and say, oh, look, circle, and then whatever, what have you, and then we could say pi r squared and everything. But okay, now we have them all back. All the names of the shapes that you knew and the formulas for the areas. But this one, this shape, this is not a named shape in human experience, right? This is not like an ellipse or something. And it definitely doesn't have you don't have a memorized formula for its area. Nevertheless, we want a formula for its area. Okay, so does everybody see what it is that we want? And furthermore, it has to be only in terms of rectangles, because rectangles is the only game in town. Okay, the way we're going to do it is like this. Okay, I'm going to make 2 copies of that shape. And, well, what I'm going to do is I'm going to cut the first one into 4 pieces. I'm going to cut it like this. Okay. So now, for each piece, we're going to do the following. We're going to find a rectangle that is the biggest rectangle that would fit entirely in here. So to be clear, like here's a rectangle. So that rectangle fits entirely in that piece there. But is that the biggest one that you can imagine? Nah, right? We can make it taller. So let's make it taller. Okay, it could go all the way up to here, right? But we can't make it any taller because then we'd start going above the red. Okay, now I want to do that in every piece. So I'll just do that real quick. Okay, so what we did is, well, if we were to take each one of these 4 rectangles, then we could find each of their areas individually, right, with like a, with our ruler. And then we could find the area of that one, that one, that one, and that one, and then we can add them all up. And that would not be exactly the correct answer, but it would be an estimate. By the way, would it be an underestimate or an overestimate? An underestimate, right? Because, well, we're missing some stuff. Okay, but you can imagine coming up with other kinds of rectangles, right? So instead of choosing the tallest rectangle that fits under the red, you could, for example, use the shortest rectangle that fits over the red. You could come up with a multitude of ways. You could choose rectangles that they hang over a little bit and under a little bit. You could do a lot of things. But at any rate, this is an estimate. And suppose that we stick with the tallest rectangle that can fit under the red. Suppose we just stick with that for now. And if we wanted a better estimate, then how could we get a better estimate? Yeah, more rectangles, right? Because if 4 is good, maybe 44 would be better. Right? So then instead of using 4, I'll use 8. Now, when I draw these pictures, I basically always, the number of pieces that I use are always going to be a power of 2, and that's because humans are good at bisecting things, which means that it's easy to double the number of pieces. So it's easy to cut something into 8 equally sized pieces, but not very easy to cut something into 7 equally sized pieces. So see, I just keep cutting the pieces in half. All right. So then, again, we'll go with the strategy that the tallest rectangle that fits under the red. Okay, so like that, 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 that. So, a better estimate, but still an underestimate, but better. Okay, well, so if 4 wasn't good enough, then we can use 8. And if 8's not good enough, we can use 88, whatever you like. For any given engineering problem, there's going to be some number that's going to be good enough, right? So like if you're trying to build a fence, okay, then you could probably do with, maybe 64 pieces. Maybe that's enough. But if you're trying to build something like a race car or an airplane engine, something that's got to be pretty accurate, then you're going to need more pieces. But for any given engineering application, you're just going to need finitely many pieces. Okay, but this is not an engineering class. This is a math class. So what we're going to do is we're going to go with the thought experiment, and we're going to wonder what it would be like if we were to just go ahead and say that there were infinitely many pieces? What would it be like if we didn't stop at 4 or at 8, or in fact at any finite number? What if we just cut it into infinitely many rectangles? Okay. Yeah, it's going to get as close to the true answer as we wish. It will, in the sense that you could say, is it within? Do you remember the epsilon delta definition of limit? Did they do that in Calculus 1? For all epsilon greater than 0, there's a delta greater than 0, such that yada yada yada. No. So we'll get to the exact answer in the sense that you could say, are we within 0.1 of the answer? And I'll say yes. And you can replace 0.1 with any number that you care to name, any positive number. So you can say, well, is it within 1/1,000,000th? Yeah. Is it within 0.1 million zeros and then a 1? Yeah. So it's exact in that sense. Fine. So, but again, what we're going to do is that we're going to find the area of that rectangle, that rectangle, that rectangle, that rectangle, that one, that one, that one, and that one, and then we're going to add them all up. And now, before I start doing the next thing, I want you to briefly consider that the very first thing that I said in this section is sigma notation. Now we're going to go to the next page. So here's the deal. Is that this is the definition of area and integral. So here we go. I'll say let f be a function on A to B. So this fancy party hat that we were talking about on the previous page is really just the graph of a function. And what we want is we want to find the area of that shape. So I'll say let n greater than 0 be an integer. And conceptually, what this is this is the number of pieces. Just like on the previous page, we drew 4 and also 8. One with n is 4 and one with n is 8. 4 pieces, 8 pieces. But the only requirement that I'm saying is that the number of pieces needs to be a positive integer. So it could be 1, it could be 1,000,000, it could be any of that. We'll define the following. Define x0 is A. Define delta x is b minus a over n. So now, conceptually speaking, x0, this is the point all the way to the left. You'll see what I mean in a moment. This is the spacing between points. Again, you'll see what I mean in just a second. xi, so now the subscript is I, as in an index. will be x0 plus I multiplied by delta x. Okay. So now this, I think, requires a picture to explain. So I'm going to take this picture and make it slightly wider so that it's easier to see. So this is point A and this is point B. But we're specifically saying that for notational purposes, we're going to refer to the left point as x0. So x0 and A are synonyms, but we're going to call it x0. Okay. And now, n is just some positive integer, but I want to draw a picture, and it's hard to draw a picture with an arbitrary number of pieces, so I'm going to just draw 4 pieces, because otherwise it might be too difficult to understand what I'm saying. So this is a picture with n equal 4 pieces. Now, here's the thing. What this is saying is that in this picture, we broke this into 4 equally sized pieces. So what is this distance right here? It is, but we've got a name for that. Delta x, right? So this, that distance there is delta x. What about what's that distance? Delta x. And that one? Delta x, okay, good. And this one's delta x too. So all those have the base of all of those little widths there are delta x. All right. So now this point is called x0. Now, if we start at x0 and then move to the right by a distance delta x, if we move 1 delta x, well, this formula is saying that if you start at x0 and move over 1 delta x, then the name of the point that you're at is x1, right? Because that's x0 plus 1 delta x. So the name of this point is x1, because you moved over from the leftmost point, you moved over 1 delta x. Now, from the leftmost point, suppose you move over 2 delta x's. 1, 2. Then what's the name of that point? x2. And the next one, x3. Good. This one is x4, but do understand that generally the rightmost point is called xn. It just so happens that in this picture we're using 4 pieces. You with me so far? Good. So now we'll choose in each interval So now, in this particular picture, there's 4 intervals in this picture, but understand that generally there are n intervals. Choose, in each interval, a sampling point which we will call Ci. Okay, so now I'll draw another picture. So is drawing this many pictures tedious? Of course it is, but I'm trying to strike a balance between tedium and intelligibility. If I was to just keep adding to the same picture, then it might not be clear exactly what I was trying to say, is what I mean. It's supposed to be the same red function. Okay. So this is x0, x1, x2, x3, and x4. So between each of them, between each of the consecutive pairs of x's, we're going to choose a value that we're calling ci. And the I corresponds to the x that's on its right. So what I mean is that the c that's in here is c1, because the x to the right is x1. Okay, and it doesn't say how to choose, so then I'm just going to choose more or less just arbitrarily. So I'll say, oh, you know, maybe this is C1 there, and then maybe exactly in the middle here is C2, not that it matters, and then maybe C3 is kind of to the left-ish, and C4 is way to the right. And so we're just sort of like arbitrarily, more or less, picking the C's. Okay. Now, evaluate F at each sample point. And form the rectangle with base delta x and height f of ci. Okay. So what that means is that I draw another copy of that picture. And this is the plot of y is f of x. Oh man. Okay, and then now those CIs, this one was a little bit over here like this, C1, C2 was right in the middle, C3 was way to the left, and C4 was way to the right. So we're now supposed to evaluate F at each of the C's. So how do you do that visually? What does it mean to visually plug one of the C's into the F function? What do you mean where the line is?
Where do you get to the C?
Uh-huh.
Go directly up to the line.
Uh-huh.
That's the value.
Yeah, right there, right? So this That's just to say, you know, from here, go straight up, right there. So that height there, that's f of C1. So now above each one of these, we need to do the same thing. Right there. Okay, so you with me so far? So now, what's the width of all these now? Delta x, right? Each one of these has a size delta x. And then we want to make the rectangles that have base delta x and height f of ci. So, well, what that means is that for each one of those green dots, just draw a line segment in between the two dashed lines. So like this. There's one. So like that rectangle has height, f of ci. That's its height. F of c1, I mean. And its base is delta x. So now we need to do the same thing with the other three rectangles. Okay, so now we've got the red curve, and we've got the green rectangles. Okay, so like for example, this rectangle that's furthest to the right, just that one right there. You know, its base is delta x, and its height is f of c4. So what's its area? Right. So I'll write it like this. So its area is f of c4 times delta x. What's the area of this one? So this one is f of c3 times delta x, and this one's f of c2 times delta x, and this one is f of c1 times delta x. Now, because I didn't choose some really obvious strategy, like make the rectangles always be under, or make the rectangles always be over, it's not entirely clear to me, just glancing at the picture, whether or not we have an overestimate or an underestimate. Right? Maybe it's over, maybe it's under, it's not entirely clear. But can we agree that it's an estimate? Can we also agree that if instead of using 4, I'd used 400, that the estimate would be better? No, I'm saying it's not clear if it is an underestimate or an overestimate, because we were just sort of randomly choosing the C's. It's just an estimate. But if we were to choose, instead of using 4, if we used more, then there would be a better estimate. Okay? Good. So now, for this specific case of 4, the estimated area would be f of c1 delta x plus f of c2 delta x plus f of c3 delta x plus f of c4 delta x. So if we add up the areas of all rectangles obtained in this way, then it would be f of c1 delta x plus f of c2 delta x plus dot 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 f of cn delta x, like so, right? I have to write n now because now we need to get back to there being n. But can we agree that this is a really tedious thing to write? Wouldn't it be excellent if we had some more compact way to write it? Wouldn't it be great? So how about the sigma notation thing? Good. So the sum from I equal 1 to n of f of c I delta x. Okay, so this is an estimate for that area using n rectangles. This is called a Riemann sum. Not that we'll really talk about that much in our class, but at any rate, Riemann is the last name of a famous dead mathematician called Bernard Riemann, because mathematicians are always naming stuff after people. Is called a Riemann sum. So now, if several requirements. First, the limit. Well, okay, let's just back up just a second. We want to express the notion of the number of rectangles becoming infinite. So currently in the picture there's 4, and then, you know, abstractly here there's n. We want the number of rectangles to become infinite. So we're going to say the limit as n goes to infinity. Right, that's saying let the number of rectangles become infinite. So if the limit of the summation from I is 1 to infinity of f of ci delta x, so if this limit exists for all possible samplings. So what I mean is that, you know, in the picture I just sort of arbitrarily chose some samples. You know, you might come up with a different way, like say, I'm always going to choose the one that's in the middle. Or I'm always going to choose the left endpoint. Or I'm always going to choose the right endpoint. Or, you know, there's just any multitudinous way to come up with a way to choose a sample. What I'm saying is that if this limit exists for every conceivable sample, like it doesn't matter how you sample, the limit's always going to exist. And 2, all such limits converge to the same value. Now this is kind of a technical matter. That just means that there's some weird functions out there where someone could say, I'm always going to choose the middle point, and someone else could say, I'm always going to choose a point that's 1/4 of the way. And these two different folks could choose their two different samplings. Both such limits could converge, but then end up converging to different values. That's kind of weird, but I just have to mention it. So if this limit exists for all possible samplings, and moreover all such limits converge to the same value, then the consequences of this is that 1, f is called integrable. On A to B. 2, the common value of those limits is called the integral of little f on A to B. And 3, the limit as n goes to infinity of the sum from I is 1 to n. Oops. Oh, look, I did it there too. that should be an n. So this thing that I'm writing in red here, that was formerly an infinity, but it needs to be an n. And this one needs to be an n. From 1 to n of f of ci delta x. So, that's kind of a mouthful to write down and say. The limit as n goes to infinity, the summation from I is 1 to n f of ci delta x. So now I get to make the oldest calculus joke that exists. Literally from the very beginning. So, here's the joke. I think I already made it at least once this semester. Well, sigma, that's from the Greek alphabet. And so's delta, right? But each one of those letters has a counterpart in the Latin alphabet. And you've got to remember that English is the Latin alphabet also. So the joke is like a pun. And what happens is that whenever you compute a limit, what happens is that the Greek symbols transform into their phonetic Latin equivalents. So what is phonetically equivalent to delta in Latin? A D, right? They both make the D sound. Okay, so that means that this is going to turn into f of x dx, like so. And then this big fancy-looking S-sounding thing, it's going to be turned into a big fancy-looking S thing. Let's make it all tall and stretched out. Fancy. And then now to indicate that this is specifically occurring, has something to do with the interval a to b, we're going to write a and b. Ta-da! I can't even tell you how funny I think that is, because this occurs all over the place in math. You know, like you can, a lot of time, like in some like super abstract math paper, you can like just guess the right answer, have no idea what you're doing, and just they're doing a limit, and well, phi is equivalent to f, so I'll change the phi to an f. Got it. Okay, so now. This is called the integral of f on the interval a to b. Now, obviously, it looks very similar to antiderivative. But you can see the way they're visually distinguished because this integral, which is not an antiderivative, has the a and the b, whereas none of the antiderivatives that we've done until now had any such thing. Okay, they're not. The integral is cutting a shape up into infinitely many infinitesimal rectangles, summing them all up, and finding the resulting value. So in particular, an integral is the result of the procedure, of the integral procedure is a number, right? It's a number. Whereas the result of the antiderivative procedure is a function, right? So if you had two machines, and you were looking at their outputs, and one of them was outputting, say, cats, and the other one was outputting galaxies, would you say that they're the same kind of thing? No, right? That one outputs cats, and that one outputs galaxies. They're not the same. The output of the integral procedure is a number. The output of the antiderivative procedure is a function. So they're not the same. But surely there must be some similarity somewhere, right? Because why else would they be written so similarly, right? Because the only visual distinguishment between antiderivative and integral is this a and b. Okay, so we've got to figure out what is it that connects them. But for now, they're just not even related. For now. Okay, so here's a question. So let y equal f of x be plotted below. So here's I'm going to make a plot here. I'm going to make this go up to like 6, so like 1, 2, 3, 4, 5, 6. And I'll make this go out to like 12 or something. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now I'm going to plot a function. And I'll say that the plot pieces, and you'll see what I mean in a second, the plot pieces are all line segments, or circle arcs. Okay, so let's say that the plot of f starts out like so. So maybe it starts out like at height 5, and it's just exactly horizontal for a little bit. All right, and it does that until 3. And then it has a jump discontinuity. Now let's not even make it have a jump discontinuity yet. Let's make it do this. So it'll just go like, you know, straight down to that one. Now maybe it has a jump discontinuity up to 2, say. And does that. And then one more jump discontinuity, it does this. Okay, so that's the plot of this function. This function is continuous except at 2 points where it has jump discontinuities. But all the various pieces, they're all line segments or arcs of a circle, meaning that you know that this is like a semicircle. All right. So now here's the request. Please evaluate the integral of f of x dx from 0 to 2, 4, 6, 8, 10, 12. 0 to 12. And here's what, in order to understand and then answer this question, you have to know the connection between integral and area. Okay, and you're allowed to use any formulas from grade school that you know. All right. This is exactly the same question that we answered 30 minutes ago. So here's the idea. Let's cut this into pieces that we could deal with in Ms. Harris's class. So here's like one piece right here. Right, just what I mean is just this much. Right? That's a rectangle. And we could, you know, you can imagine just cutting it out and then measuring it. Okay, we could do that. I see that the base is 3 and the height is 5. Okay, then what's the next piece you might cut out? A triangle. Okay, so then do that. So this. Here the base is 2, and again the height is 5. Then we might cut out that little rectangle there. Base 3, height 2. And then that half of a circle there. So where circles are concerned, well, and our formulas for their areas are concerned, the interesting measure is not this whole thing, but what? Half of that, right? The radius. So then the radius would be 2. So can you see that we can sort of cut this into grade school pieces? Okay. Well, the formula here would be, base times height. For this one, it would be base times height, and then over 2, because the over 2 comes from the fact that it's a triangle. For the next one, again, base times height. And then for the last one, what would be the formula? Right? Pi times the radius squared, but that's not the whole story. What else do we need to do? Divide by 2, because it's half of a circle. Right, and then you could simplify this. Any question about this? What if I was to ask for, say, something like this? Say the integral from 3 to, what am I trying to say? 3 to 8. Is it the same answer as before? Okay, if it's not the same answer as before, then why not? Right, because this one was saying, I want you to proceed all the way from x is 0 to x is 12. So in a sense, the whole thing there. But this one is saying that actually I'm only interested in the interval 3 to 8. So there could be lots of stuff that comes before 3 and lots of stuff that comes after 8. But I'm just interested in the stuff between 3 and 8. So in this case, the answer would be, just the triangle and the rectangle. Good. Any question about this? So one of the most common errors, besides having no idea what to do on this exercise, is I'll give something like this. I'll give some picture, and then I'll give an integral, and student responds with what would be the integral of the whole thing, but I only asked for part of it. That's one of the most common categories of error. Any question about this? Yeah? That's the exact area. Mm-hmm. Mm-hmm.
So with this hard distinction between integral and antiderivative, when people say indefinite integral, and they're talking about...
We'll get to that.
Okay.
We'll get to it. Another thing is that if you look at our definition of area and the Riemann sums and things like that, did you have a question?
Yes.
What's up?
The line that you did, that's 2 times 3, is that supposed to be, I think I was confused on that one. Is that rectangle? Right?
This?
Yeah.
Yeah, because what I like between 1, 2, 3, 4, 5, and 6, 7, 8. Between 5 and 8,
Mm-hmm.
what is that shape?
It's a rectangle, so we're, okay, I got you.
Yeah, you can imagine if you like that there's like a dashed lines right there.
Yeah, makes sense.
So again, going back to the definition of Riemann sum and things like that. Now, as it happens, I drew a picture like this so it would be intelligible. And one of the ways I made it as intelligible as possible is I drew a function, all of whose outputs were positive. So you can see that they're positive because they're above the x-axis. So the outputs are positive. But in fact, nothing about the definition requires positivity of the function, right? So what that means is that, among other things, is that it's perfectly intelligible and meaningful to have something with a negative area. Now, that's a little bit disturbing for first-year calculus students to take in, that something could have a negative area. But I hope to convince you in the next 2 or 3 minutes that that's a perfectly reasonable thing. So specifically, in the first place, those definitions are saying that if something looks like this, if we have a function that does this business, and that's the plot of f, then the parts of f that are above the x-axis, that's where f is positive, and the parts of f where it's below the axis, that's where f is negative. Now, that means that this area that is above the x-axis, where the integral is concerned, will be construed as a positive area, and this area that is underneath the axis, a negative area. Now, Walmart, you heard of those guys? They make a lot of money, and they're everywhere. I'm not like being, like mysterious. I'm talking about you could drive down the street and you could just walk into a Walmart. Okay, so it might surprise you to find out that between the hours of like 2 a.m. and 5 a.m. in the morning, Walmart's actually losing money. Like, and not like a little bit of money, but like a lot, like thousands and thousands of dollars an hour. They're losing money. They're losing money because, well, in the end, they're just not making very many sales during that time. But nevertheless, they have to pay the cost of, keeping things up. Like, most Walmarts these days, they have produce, like vegetables and stuff. You can't just turn off the freezers and the air conditioners and stuff when people aren't there. The stuff will ruin, right? You got to keep running that stuff, otherwise it's no good. Furthermore, a significant amount of Walmart's labor is actually spent when there's no one shopping, because they take that time to restock the shelves and reorganize the store. So one of the biggest times of labor cost of Walmart is when there's no sales occurring whatsoever. Okay, so it is literally true to say that every single Walmart retail store loses a great deal of money every day, at least during the hours from 2 to 5 in the morning. Then why even have a Walmart if they're losing money so regularly every day? Why not just shutter them all up and just forget the whole thing? Oh, they make more during the day, right? To cover the loss. So now, so Walmart loses money between 2 and 5 in the morning. But maybe you'll forgive me just slightly for being a mathematician and saying, would you agree that they make negative money during the hours of 2 and 5 in the morning? Yeah, okay. That's kind of a weird way to say it. They make negative money. Instead of saying they lose money, well, they make negative money. All right. So, if you were to consider average over the whole day, they make They make positive money every day. That's why they remain open, even if it is the case that for several hours every day that in fact they're making negative money. This is the time of day that they're making money. Positive inflow. They're making so much money per hour, and they get that much, and then they're making so much negative money per hour, and this is their loss during that time. But should Walmart remain in business? Why? Because the positive bit is more than the negative bit. So I promise you it makes perfectly intelligible sense to talk about negative areas. In the same kind of sense, and in the same exact way as we can accept that Walmart makes a negative amount of money during the hours of 2 and 5 in the morning, or if you like, a loss. Okay, as a result, I can give you a question just like the one above, where instead of making all of the grade school shapes be above the axis, some of them are below the axis. So I can give you one that looks like this, say. I give you like a circle, and then a slightly smaller circle. It's like that, and then a triangle, and then a rectangle, and then a little triangle like this. Just some kind of grade school nonsense. Okay, then I could say, well, I want you to integrate. I want you to integrate this function over the whole span, say. So that's what you should do then, is find the area of that bit, and the area of this bit, and the area of this bit, and the area of this bit, and the area of that bit. So you find each of their areas individually using your grade school formulas, and then now you have to remember that which ones of these are going to be reckoned as being positive and which reckoned as negative. So which ones are going to be reckoned positive? The ones above. So these are positive areas. And these ones down here are negative areas. Okay. Any question about this? Good. So, last thing we're going to say before we have a quiz, because we have a quiz today, is the following: is that okay? So now in this class, well, I guess I have to say two things actually. In this class, we've written things that look like this. And we've just now written things that look like this. And these things are different enough that I'm enforcing the use of extremely different names for them. So in particular, when you do this, the result of a computation like this is a function, whereas the result of a computation like that is a number. This kind of thing we're calling antiderivative. And this thing we're calling integral. Now, in your book, and probably in your previous calculus courses, this kind of thing was referred to as an indefinite integral. And this thing is referred to as a definite integral. So it is just fine for you to use the green terminologies, but I will not. I will refer to them as antiderivative and integral. And I can't even express to you the depth of loathing that I feel for instructors and textbooks who use the green terminology. I think it is an ugly and callous thing to students, because what it does is it makes it difficult to understand just how different these things are, because you're calling them the same name but only changing an adjective, indefinite and definite. They're utterly different kinds of things. This kind of thing outputs a function. That kind of thing outputs a number. Now, these things are intimately related, because otherwise, we wouldn't stomach, we wouldn't suffer the fact that they look so similar. So, what I'm going to do is I'm going to foreshadow what we're going to talk about next time. So, this is called the fundamental theorem of calculus. And it's the reason why calculus. It's the reason I suspect the green language even exists at all. So we can say the following. If 1, the derivative of big F is little f. So now, that means that we have two functions, a big F and a little f, and they're related to each other in this differential relationship that the derivative of the big one is the little one. If we were to move the derivative to the other side, then what does it become when you move derivative to the other side? So just like if we had an equation that looked like 3x equals y, yeah, antiderivative, right? When you move that over, so like if there was a multiply by 3 and you want to get it on the other side, it's a divide by 3 on the other side of the equation. Here on this side, it's a derivative. If you want to get it on the other side, it's antiderivative. So understand that this is just another way to say that the antiderivative of little f is big F plus a constant. These two things are the same thing. And 2, that little f is integrable on the interval a to b. So if little f can be integrated, and furthermore, big F is an antiderivative of little f, if those two things are true, then this, the integral, is equal to, now I'm going to pause here, and what I want to point out is that the three major notions in calculus are all written on the page currently. Derivative, antiderivative, integral. The three major different notions are all written on the page. Furthermore, we just defined this notion. We just defined it, and what it is, what its definition is it's saying that we're going to take the shape that's defined by, between x's a and b, bounding a shape with f of x, and then we're going to take that shape, we're going to cut it up into rectangles and compute an estimate for the resulting area. And then we're going to have to let the number of rectangles become infinite so that each rectangle becomes infinitesimal. We're going to find all the areas of those infinitesimal rectangles, sum them all up, and that's the integral. That's a mouthful. That's what this is saying. You've got a lot of stuff to do if you're going to carry that out. The fundamental theorem of calculus is saying that, well, if the thing that you're integrating is integrable and, in fact, so nice that you have an antiderivative, then it's not necessary to cut anything up. You don't need to do any such thing. In fact, you just need to do three things. You evaluate the antiderivative once. You evaluate the antiderivative twice. And then you take those two evaluations and you subtract them. And that's all that you have to do. You don't have to cut stuff into rectangles. You don't have to do nothing. You just evaluate the antiderivative twice and subtract those two evaluations. No rectangles. I can't even explain to you the unfathomable depths of surprise that this causes me every time I think about it. But then I, remember how it's proved, and I say, yeah, it's got to be that way. It couldn't be any other way. All three notions in calculus, all three major notions written on the page, summarized with one little formula. It's beautiful. So the reason why this language is used is because these are actually completely different notions, but you can use the antiderivative to compute an integral if the thing you are integrating is antidifferentiable and you know what its antiderivative is. So what I'm telling you is that this kind of thing is used to carry that out, but only when you can do this kind of thing, and you can't always. Okay, so we'll talk more about what that means next time, but for now it's time for a quiz.